In this video, we're going to learn about the graphical behavior of polynomials. Let's first review what a zero or root is. So graphically, this is where f of x or y crosses the x-axis. In other words, a zero is wherever y is 0. So these would be our x-intercepts in our graph. Algebraically, these are the x values where y equals 0. So if you're asked to find this algebraically, you would set y equal to 0 and then find x. So let's look at an example. We're asked to identify the zeros of x squared minus 2x minus 3, both graphically and algebraically. Here's a graph of that quadratic function. If you look at the graph, when we're trying to figure out the zeros, we want to see where y is 0. Since y is 0, we don't say y equals 0. Instead, we say what the x values are. So the x values where y is 0 are at -1 and 3. So those would be our zeros, -1 and 3. If we were to try to find this algebraically, we would set this function equal to 0. So we would write 0 equals x squared minus 2x minus 3. And then we would solve this quadratic equation. You could either use the quadratic formula or you could factor. Here, factoring would be easier. So we factor it, and since we have a product of two factors that equal 0, that means that at least one of these factors has to be 0. So we set each factor equal to 0, and then we solve for x. And again, we would get that x is 3 or -1. Next thing we're going to talk about are the number of terms of polynomials. So we're going to try to figure out a general rule, and to do this we're going to look at a few examples. So let's first talk about quadratic functions. They have at most 2 zeros. So if you think back to Algebra 2, you'll recall that the discriminant from the quadratic formula tells you if a quadratic has 2, 1, or 0 real roots. Here are a few examples to help us remember this. So our first example is x squared plus x minus 6. If you factored that, you would find that you have two different roots. Here they would be 2 and -3, since those are the x values that make each factor 0. And if you graphed this, you would see that your quadratic crosses the x-axis twice. Our next example is -4x squared plus 4x minus 1. If we factored this, you would see that you have a repeated root. In other words, here the root would be -1/2, because that's the x value that would make each factor 0. And if you graphed this, you would see that your quadratic only touches the x-axis once, so it only has one root. Our last example is x squared plus 4x plus 5. This actually has no real roots. It would have two imaginary roots, but if you graphed it, you would see that the quadratic doesn't cross the x-axis anywhere, so there are no real zeros. In general, if we think about the maximum number of turns for any quadratic, the maximum number is going to be 1. And all a turn means is how many places the quadratic changes directions. Alright, so just to recap, a quadratic polynomial, which has degree 2, has at most 2 zeros and at most 1 turn. Let's now look at cubic functions and see if we find a pattern here. So a cubic function will have at most 3 zeros. And let's see a couple examples. So first of all, if we have x cubed minus 9x, and we factored this, we would get x times x minus 3 times x plus 3. And the way I factored this was I first pulled out the greatest common factor of x, and then you would be left with x squared minus 9, which is a difference of squares that you would factor. Here the zeros would be 0, 3, and -3, because those are the x values that make each of those three factors become 0. And if you graphed x cubed minus 9x, you would see that this graph crosses the x-axis in 3 places, and those would be at -3, 0, and 3. Another example is x cubed. If you factored this, it's really x times x times x. So for each of those factors, the 0 would be 0, and this factor occurs 3 times, so we would say that's a triple zero, or a triple root. And if you graph that, you'll see that the only 0 there is at 0. All right, so what was the maximum number of turns here? Well, in our first graph, our cubic function actually has 2 turns. It changes direction twice. In our second graph, it doesn't have any turns. So it looks like the maximum number of turns for a cubic polynomial would just be 2. So now we're asked, a polynomial of degree n will have at most how many zeros and how many terms? So thinking back to the last slide, our quadratic, which was degree 2, had at most 2 zeros and at most 1 term. And here, a cubic polynomial, which is degree 3, has at most 3 zeros and at most 2 terms. So the pattern seems to be that the degree and maximum number of zeros match each other, and then the maximum number of turns is going to be 1 fewer than the degree. So if the degree is n, we would say it would have at most n zeros and at most n minus 1 terms. Let's now talk about multiplicity. All this means is how many times a 0 or root appears. So here are 2 graphs. On the left, I have a graph of a couple different power functions that all have even degrees, and the graph on the right are power functions with odd degrees. So in both of these graphs, all those functions have a 0 at 0, meaning that when x is 0, that's where our y value is 0. So let's try to think about what's happening with the graphs. When the power is even, so when a 0 reappears an even number of times, we notice that the graph kind of rebounds at the 0. For instance, if you look at x squared, that has a double repeated 0 of 0. X to the 4th, if you factor that, you'd have x multiplied out 4 times, and if you set each factor equal to 0, you would have 4 zeros at 0. But both times, the graph approaches the 0 and then bounces back in the direction it came from. Whereas when the 0 repeats an odd number of times, the graph crosses at the x-axis. We're going to find one more pattern. So if we graphed y equals x, that has a single 0 when x is 0. If we graphed y equals x cubed, that's a triple root when x equals 0. If you compare the shape of these, you'll notice that something different happens. So when we graph x equals cubed, it crosses through just like y equals x, but it has that inflection point at the 0. So let's summarize what just happened with multiplicity. So basically what this is saying, if you look at the far left at the bottom, if you have a single 0 or single root, in other words, it has a multiplicity of 1, your polynomial will just cross right through at that 0. If you have a multiplicity of 2, or a double root, or actually any even multiplicity, so multiplicity of 4, multiplicity of 6, your graph will touch the 0 but then bounce back to the direction it came from. And if you have any odd repetition of a root, so a triple 0, a 0 that appears 5 times, your graph will cross through just like with a multiplicity of 1, but the shape changes and you get an inflection point. Let's talk about extrema. All that means is a maximum or minimum on your graph. So we already saw some turns, and that's one type of extrema. A graph might not have any maxima or minima. There are 2 categories for extrema. They can either be local or relative, which is pretty much just any max or min, or it can be global or absolute, and this would be the largest value that the function has or the smallest value that the function has. And this infinity and negative infinity aren't considered a global maximum or minimum. So let's look at an example. So here we have some polynomial function, and it looks like it stops at the end. Let's just look at each x value and try to describe whether we have a local max, a local min, or an absolute max or min. So if we look at when x is a, that value is larger than the other values to the right of it. So that would be a local max. If we look at b, that would be a local minimum, because to the left and the right of b, the graph is then bigger. So basically, anytime you hit what looks like a valley in the graph, that's a local min, and if you hit something that looks like a peak, that's a local max. If we look at c, that's going to be a local max, that looks like a peak. D would be a local min, because that looks like a valley. E would be another local max. F would be another local min, and actually f is the smallest of these minimums, so we would call that our global or absolute min. G is another peak, so that would be a local max. H is another valley, that would be our local minimum. I is another peak, so that would be a local max. Also, I is the largest maximum, so that would be our global or absolute max. And J would be a local minimum, because a little bit to the left of J, the graph is bigger, so J is the smallest value in that immediate interval. And this chart just summarizes what we just had. Let's look at an example with a graph. So here we have a cubic polynomial, and we're asked to identify the different kinds of extrema. So let's first notice that when x is -1, there is a peak in the graph. So that's going to be a local max. So we would say we have a local max at the point -1, 0. When x is 1, we see that the graph hits a valley. So that would be a local minimum. So we would say we have a local min at 1, -4. Now if you notice, there's no one value that's the largest value on the graph, because the graph goes up forever to the right. And if you look at the left, the graph goes down forever. So there's also no one minimum value. So here we would say that there is no absolute extrema.